Astronomers just found something the universe was never supposed to have: a galaxy cluster burning at over 100 million degrees Celsius, existing just 1.4 billion years after the Big Bang. ALMA confirmed the signal, and every single cosmological model currently in use fails to explain how this is possible. Right now, 12.4 billion light-years away, a structure called SPT 234956 is doing things that should take billions of years to happen. It already happened in less than one. The intra-cluster gas temperature exceeds 10 million Kelvin. Current models predicted it should be at least 5 times cooler at this stage of cosmic history. The thermal signal was so strong that the lead researcher initially rejected it as a measurement error. Over 30 galaxies are packed into a region just 500,000 light-years across, forming new stars at a rate 5,000 times faster than the Milky Way. That density and that rate of stellar production should not coexist in a structure this young. All current simulations produce 0 objects with these properties at this epoch. 3 supermassive black holes are already active inside this cluster, firing jets and injecting energy at a scale no formation model predicted for the first 1.4 billion years of the universe. The combined probability of all these conditions existing together this early is, by every simulation we have run, effectively 0. Lead author Daji Zhou from the University of British Columbia stated in January 2026. In fact, at first I was skeptical about the signal as it was too strong to be real. But after months of verification, we confirmed this gas is at least 5 times hotter than predicted. Still more disturbing, SPT 234956 is not a protocluster. It is already gravitationally bound. It already has a stable structure. Every single protocluster found at comparable distances was still collapsing. SPT 234956 finished that process early. SPT 234956 broke every rule we use to calculate how fast the universe builds its largest structures. Here is what should concern you most. If this cluster formed this quickly and this violently, the lambda cold dark matter model, the standard framework that governs our entire understanding of how the universe evolved, may need to be fundamentally rewritten. Think about that. Before we go deeper into what this discovery actually means, if you want to stay updated on what may be the most important challenge to cosmological models in the last decade, hit subscribe and turn on notifications, because what we are about to break down will completely change how you understand the formation of the universe's largest structures. Leave a comment telling us, do you think the early universe was far more violent than we ever imagined? Or is there a simpler explanation scientists are missing? Let's start with what SPT 234956 actually is. On the surface, it looks like a galaxy cluster, a gravitationally bound collection of galaxies sharing a common center of mass. That is not unusual. Galaxy clusters are the largest structures in the universe. There are thousands of them within observable range. But SPT 234956 is not normal in any measurable way. It sits at a redshift of 4.3. That single number tells us exactly how far back in cosmic time we are looking. Redshift 4.3 corresponds to a look-back distance of 12.4 billion light-years. The universe was 1.4 billion years old when the light we are detecting now left this object. The universe is currently 13.8 billion years old. SPT 234956 existed when the cosmos was roughly 10% of its current age. To put that in perspective, our own Milky Way did not finish assembling until the universe was at least 8 billion years old. SPT 234956 was already a fully formed, gravitationally bound, superheated structure when the universe was 1/10 as old as it is now. But the mysteries don't stop there. SPT 234956 was first detected in 2010 by the South Pole Telescope. That instrument sits at the geographic South Pole in Antarctica and scans the sky at millimeter wavelengths. At that stage, SPT 234956 appeared as a faint but unusually bright point source in the submillimeter catalog. Bright enough to flag as anomalous, not bright enough to understand. Follow-up observations began immediately, but the object stayed out of reach of the instruments that could resolve its internal structure. For 8 years, it remained a bright smudge. Extraordinary by any measure, but unexplained. Then ALMA changed everything. In 2018, the Atacama Large Millimeter-Submillimeter Array conducted high-resolution imaging of SPT 234956. ALMA is a network of 66 radio antenna dishes spread across the Atacama Desert in Chile, sitting at an altitude of over 5,000 meters. Working in concert, the array achieves angular resolution that no single telescope on Earth can match at these wavelengths. What ALMA revealed was already extraordinary. SPT 234956 was not one object, it was a collision. 14 galaxies, all detected in submillimeter light, packed into a volume just 3 times the diameter of the Milky Way. Each of those galaxies was classified as a submillimeter galaxy, one of the most luminous, dust-obscured, rapidly star-forming types of galaxy known to exist. A single submillimeter galaxy can outshine a trillion suns. 14 of them crammed together, actively merging. The integrated star formation rate across the cluster exceeded 10,000 solar masses per year. That means SPT 234956 was converting raw gas into new stars at a rate that would exhaust the entire gas supply of a normal galaxy in less than 1 million years. Our own Milky Way produces roughly 1 to 2 solar masses of new stars per year. SPT 234956 was producing between 5,000 and 10,000 times that amount. Scott Chapman, then at the National Research Council of Canada, stated at the time, "Having caught a massive galaxy cluster in the throes of formation is spectacular in and of itself. But the fact that this is happening so early in the history of the universe poses a formidable challenge to our present-day understanding." Here's where it gets really strange. By 2024, observations with the Chandra X-ray Observatory had detected at least 2 active supermassive black holes inside SPT 234956. One of them, designated C1, had an X-ray luminosity of 2 times 10 to the power of 45 ergs per second. That number is comparable to the brightest quasars ever observed at any distance in the universe. And C1 was Compton thick, meaning the black hole was so heavily surrounded by gas that only the most energetic X-ray photons could escape detection. The black hole powering C1 was estimated at over 600 million solar masses. It had already grown to that size in less than 1.4 billion years. Standard accretion models suggest growing a black hole to 600 million solar masses from a stellar mass seed should take at least 3 to 5 billion years under optimal conditions. Something accelerated that growth dramatically. A third supermassive black hole was confirmed through radio observations with the Meerkat telescope, showing elongated jet structures at 5.5 and 9.0 gigahertz. 3 supermassive black holes, all active, all firing jets, all inside the same infant cluster. The black hole growth problem is one of the most difficult puzzles in early universe astrophysics. Standard models assume black holes begin as stellar remnants, collapsed cores of massive stars that lived fast and died young. A stellar mass black hole starts at roughly 10 to 100 solar masses. To reach 600 million solar masses, it must accrete and consume surrounding material continuously at near maximum rates for billions of years. That maximum rate is called the Eddington limit, the point where radiation pressure from infalling matter pushes back hard enough to halt further accretion. C1 in SPT 234956 appears to have sustained accretion at or near the Eddington limit for an extended period. That is not impossible in principle, but doing it consistently enough to produce a 600 million solar mass black hole in under 1.4 billion years requires either an extraordinarily massive seed, far heavier than any stellar remnant, or accretion physics that current models do not fully account for. Some researchers have proposed that the first black holes in the universe formed not from collapsed stars, but from the direct collapse of massive gas clouds, producing seeds of 100,000 to 1,000,000 solar masses from the start. If that mechanism operated inside SPT 2349-56, it would explain the black hole masses. But direct collapsed black holes remain theoretical. No one has confirmed one. And then something that no model had predicted happened. On January 5, 2026, Daji Zhou and his international team published their results in the journal Nature. The paper title was direct: Sunyaev-Zeldovich detection of hot intracluster gas at Redshift 4.3. The key to the discovery was a technique called the thermal Sunyaev-Zeldovich effect. This is not a direct observation of the gas itself. It is an indirect measurement, and it is extraordinarily precise. Here is how it works. After the Big Bang, the universe cooled enough for light to travel freely for the first time. That light still exists today as a faint, uniform glow filling all of space. It is called the cosmic microwave background, or CMB. The CMB is the oldest light in the universe, a snapshot from 380,000 years after the Big Bang. When CMB photons pass through a galaxy cluster, they interact with hot electrons in the intracluster gas. Those hot electrons transfer energy to the photons through inverse Compton scattering. The photons gain energy. Their wavelength shifts. This creates a measurable distortion in the CMB at the exact location of the cluster. The hotter the gas, the more energetic the electrons, and the stronger the distortion. The Sunyaev-Zeldovich effect is essentially a thermometer for the universe, reading temperatures billions of light years away with no physical contact required. Zhou's team pointed ALMA at SPT 234956 and measured this distortion. The signal, in Zhou's own words, was too strong to be real. Here is where the physics we thought we understood stops working as expected. For months, the team ran verification checks. They recalibrated instruments. They tested for systematic errors. They compared their results against known clusters at different distances. Every single check confirmed the same finding. The thermal Sunyaev-Zeldovich signal from SPT 234956 indicated an intracluster medium temperature exceeding 10 million Kelvin. Some analyses place it above 100 million degrees Celsius. Those numbers are not unusual for mature galaxy clusters in the present-day universe. The Coma cluster, one of the nearest massive clusters to Earth, has gas temperatures around 80 million Kelvin. The Perseus cluster reaches similar values, but Coma and Perseus are billions of years old. They formed through billions of years of gravitational collapse, merger events, and accretion shocks. Each collision between infalling galaxies converts kinetic energy into thermal energy. Over cosmic time, that process heats the intracluster gas to the temperatures we observe today. SPT 234956 achieved comparable temperatures in 1.4 billion years. Models predicted the gas should still be relatively cool at this stage. Not cool by human standards, cool by cluster standards. Simulations expected temperatures around 2 million Kelvin or less for a structure this young. The observed temperature is at least 5 times higher than that prediction, and the data showed something that no current computational model could reproduce. The energy budget does not balance. Gravitational heating alone, the standard mechanism by which intracluster gas reaches high temperatures, cannot account for the thermal energy measured in SPT 234956. The calculation is straightforward. The amount of energy stored in the hot gas exceeds what gravitational collapse of the known member galaxies could have deposited over 1.4 billion years. To make that concrete, in the Perseus cluster, one of the best studied nearby clusters, the central supermassive black hole fires jets roughly every 10 million years. Each burst deposits energy equivalent to millions of years of the sun's total output into the surrounding gas. Perseus has had billions of years to run that cycle. SPT 234956 has had less than 1.4 billion years, and it has already reached comparable thermal states. 3 black holes running that cycle simultaneously at higher accretion rates in a much denser environment could theoretically produce the observed temperatures. But that scenario requires all 3 black holes to have been active from very early in the cluster's existence. There is no cooling period, no gradual ramp-up. The energy injection had to begin almost immediately after the cluster started forming. Something else is injecting energy into this system. Something powerful, something fast. The leading explanation points directly at the 3 supermassive black holes. Active supermassive black holes produce jets. These are collimated streams of plasma and magnetic fields, accelerated to near light speeds and launched from the poles of the black hole's accretion disk. When those jets strike surrounding gas, they transfer enormous amounts of kinetic energy into the intracluster medium. This process is called AGN feedback, and it is one of the most powerful energy injection mechanisms known in astrophysics. In mature clusters, AGN feedback is well documented. It regulates star formation, prevents gas from cooling, and maintains the thermal state of the intracluster medium. But in those clusters, the process develops gradually over billions of years as the black holes grow and the cluster stabilizes. In SPT 2349-56, 3 black holes are already active, already firing jets, already depositing energy into the surrounding gas at a rate the cluster has not had time to reach through standard gravitational processes alone, Dr. Scott Chapman stated in January 2026. This tells us that something in the early universe, likely 3 recently discovered supermassive black holes in the cluster, were already pumping huge amounts of energy into the surroundings and shaping the young cluster, much earlier and more strongly than we thought. But there's another problem that nobody is discussing. The standard cosmological model, lambda cold dark matter, describes how matter clumps together after the Big Bang to form galaxies, clusters, and the large-scale structure of the universe. It has been extraordinarily successful at predicting observations on scales ranging from the cosmic microwave background to the distribution of galaxy clusters across billions of light years. But lambda cold dark matter assumes a specific timeline for structure formation. Dark matter halos form first. Gas falls in. Stars form. Black holes grow. Clusters heat up. Each step depends on the previous one. Each step takes time. SPT 234956 compressed multiple steps of that timeline into a fraction of the predicted duration. The cluster is already gravitationally bound. The black holes are already massive. The gas is already superheated, all at redshift 4.3, when the universe was 10% of its current age. Chu stated, SPT 234956 changes everything we thought we understood. Our measurements show a superheated cluster atmosphere only 1.4 billion years after the Big Bang, at a time when we thought the intracluster gas should still be relatively cool and slowly settling in. It suggests that the birth of massive clusters could be much more violent and efficient at heating the gas than our models assumed. Here is where the comparison becomes uncomfortable. SPT 234956 is not the only early universe structure that has surprised astronomers. The James Webb Space Telescope has repeatedly found galaxies in the first billion years of cosmic history that are far more massive than models predict. In 2023, JWST identified a protocluster called A2744Z7P9OD just 650 million years after the Big Bang. In 2019, astronomers found Z660D at 770 million years post-Big Bang. The critical difference is this: those earlier structures are protoclusters. They are not yet gravitationally bound. Their gas has not yet heated up. They are still in the process of collapse. SPT 234956 is past that stage entirely. It is already bound, already hot, already thermally stable enough to produce a Sunyaev-Zeldovich signal detectable across 12.4 billion light-years of space. No protocluster found at a comparable distance has shown this level of thermal maturity. The observational gap between SPT 234956 and every other known structure at this epoch is significant. The gravitational binding status is the single sharpest dividing line in this story. A protocluster is a collection of galaxies that are falling toward each other but have not yet reached a stable, self-sustaining gravitational equilibrium. The galaxies are still moving inward, the gas is still settling, the structure is still being assembled. That process, in standard models, takes hundreds of millions to billions of years after the initial overdensity forms. SPT 234956 completed it. The cluster has a velocity dispersion of approximately 500 kilometers per second across its member galaxies, implying a virial mass of around 2 × 10 to the power of 13 solar masses. That is the signature of a gravitationally bound system, not a system in the process of becoming bound, a system that has already finished that transition. At redshift 4.3, that transition should not have happened yet according to standard formation models. The fact that it did means either the initial overdensity was far denser than models predict, or the collapse happened far faster than gravitational dynamics alone would allow. And the numbers showed something that no one expected. Prior to this observation, hot cluster atmospheres had not been directly detected within the first 3 billion years of the universe's history. SPT 234956 pushed that detection back by 1.6 billion years in a single measurement. The signal was not marginal. It was, as the researchers described, unambiguous. Joe stated, "We see intense star formation, energetic supermassive black holes, and this overheated atmosphere all packed into a young, compact cluster. There is still a huge observational gap between this violent early stage and the calmer clusters we see later on. Here is the calculation that should make you uncomfortable. SPT 234956 contains over 30 galaxies forming stars at 5,000 times the Milky Way's rate. 3 supermassive black holes are actively firing jets. The gas temperature exceeds predictions by a factor of 5. And the entire structure is gravitationally bound at an age when models say it should still be falling apart. Each of those facts individually represents an extreme outlier. Taken together, they define a structure that sits outside the parameter space of every published cosmological simulation." Chapman stated, "It suggests that the birth of massive clusters could be much more violent and efficient at heating the gas than our models assumed. The question the data forces us to ask is not whether SPT 234956 is unusual. It is whether it is unique. ALMA detected SPT-234956 because it was extraordinarily bright in sub-millimeter wavelengths. Most protoclusters at comparable distances are far fainter. Current surveys have only begun to explore the sky at the sensitivities required to find objects like this one. The South Pole Telescope survey that first flagged SPT-234956 covered 2,500 square degrees of sky. The full celestial sphere contains over 41,000 square degrees. The next generation of radio arrays will change that picture dramatically. The Square Kilometre Array, currently under construction across South Africa and Australia, will achieve sensitivity levels orders of magnitude beyond current instruments. It will be capable of detecting Sunyaev-Zeldovich signals from clusters at redshifts above 5, deeper into the universe's infancy than any existing telescope can reach. The SKA's total collecting area will be roughly 1 square kilometer of antenna surface, distributed across baselines stretching thousands of kilometers. At those sensitivities, surveys will be able to measure intracluster gas temperatures in clusters containing as few as a handful of galaxies at the highest redshifts. That is a capability we do not currently have. Right now, detecting the thermal Sunyaev-Zeldovich effect requires objects as extraordinarily bright as SPT-234956. The SKA will make that measurement routine. If those surveys find more structures like SPT-234956, the implications compound rapidly. The standard timeline for cluster formation would need to be revised. The role of early black hole activity in heating the intracluster medium would need to be elevated from a secondary effect to a primary driver. And the lambda cold dark matter model would face pressure from a completely new direction. Now let's put everything together. SPT-234956 exists at redshift 4.3 when the universe was just 1.4 billion years old. It contains over 30 galaxies packed into 500,000 light years. It is producing stars at 5,000 times the rate of the Milky Way. 3 supermassive black holes are actively firing jets. The intracluster gas exceeds 10 million Kelvin, at least 5 times hotter than any model predicted for this epoch. It is already gravitationally bound, a stage that protoclusters at comparable distances have not yet reached, and no current simulation has ever produced an object matching these properties at this age. The combined probability of all these conditions coexisting at redshift 4.3, according to every lambda cold dark matter simulation run to date, has no precedent. 0 published models generate a structure like SPT-234956 this early. We are not saying that SPT-234956 proves the standard cosmological model is wrong. The scientific consensus acknowledges that AGN feedback from early black holes is a plausible energy source, and that models likely underestimated how quickly black holes could grow and activate in extremely dense environments. But we have reached a point where even the researchers who made this discovery are stating that the formation timeline needs to be fundamentally reconsidered. Joe stated, "There is still a huge observational gap between this violent early stage and the calmer clusters we see later on. Mapping how their atmospheres evolve over cosmic time will be a very exciting direction for future work." And here is what this really means. The early universe was not the quiet, gradually assembling structure that cosmological models have assumed for decades. It was violent. Structures formed faster, burned hotter, and reached maturity earlier than any current prediction allows. And the black holes at their centers were already active, already powerful, already reshaping their surroundings, long before the models said they should exist. So what do we know for certain? SPT-234956 is a gravitationally bound galaxy cluster at redshift 4.3, confirmed by ALMA observations. Its intracluster gas temperature exceeds 10 million Kelvin, measured through the thermal Sunyaev-Zeldovich effect. 3 supermassive black holes are actively injecting energy into the cluster. The discovery was published in Nature on January 5, 2026, by an international team led by the University of British Columbia. What don't we know? How did 3 supermassive black holes grow to hundreds of millions of solar masses in less than 1.4 billion years? Is SPT-234956 a rare outlier, or is it representative of a class of early universe structures we have barely begun to detect? How does AGN feedback operate differently in the first billion years of cosmic history compared to later epochs? And what does this force us to revise in the lambda cold dark matter model? And here is the urgency. The Square Kilometre Array is scheduled to begin science operations within the next few years. Its survey capabilities will detect thermal signatures in distant clusters at sensitivities no current instrument can match. The Vera Rubin Observatory will add optical depth to those surveys. Together, they will begin cataloging the thermal properties of clusters across the first 2 billion years of cosmic history within this decade. Because if SPT 234956 is not unique, if other clusters heated this fast and reached this level of maturity this early, then every timeline we have used to predict when the universe's largest structures first appeared needs to be recalculated from scratch. The truth is this: SPT 234956 did not just challenge a prediction. It challenged the assumption that structure formation in the early universe followed the same gradual, well-ordered process we observe in the present-day cosmos. The early universe built its largest structures faster, hotter, and more violently than we thought possible. And the only way to find out how common that was is to keep looking deeper, earlier, and with instruments powerful enough to detect the thermal signatures of clusters that formed when the universe was barely alive. If this discovery changed how you think about the universe's earliest history, hit like and subscribe to this channel. We are tracking early universe anomalies in real time, and you will not want to miss what the square kilometer array reveals about the first billion years of cosmic structure formation. Leave a comment with your take. Do you think the early universe was fundamentally more violent than our models assume? Or will new data eventually bring SPT 234956 back in line with standard predictions? And share this video with anyone who thinks cosmology has all the answers figured out. After this, they will never look at galaxy clusters the same way again.